Hello, everyone. My name is Aydin Nasirzadə, and I am honored to present our latest research titled AI-Driven Fault Detection using LoRaWAN in Solar-Powered Microgrids for Agricultural Irrigation Systems. The work has been carried out in collaboration with my colleagues İlkin Balazadeh, Aygül Musayeva, and Tural Aliyev. Solar-powered microgrids are proving to be a sustainable and practical energy source for irrigation, especially in remote farming areas where traditional power isn't really available. But when things go wrong, for example, a sensor stops working, a wire gets damaged, or there's a communication problem. Now, all these things can interrupt irrigation. It can waste water. It can even harm the crops. Unfortunately, most traditional fault detection systems rely on fixed rules or thresholds, right? Now, this often generates too many false alarms, or even worse, they miss slow or unusual faults altogether. In our research, we present a smarter approach, an AI-based fault detection system that uses LoRaWAN, of course, for long-range communication, and LSTM neural networks to spot issues in real time, adapting as the system conditions change. We are talking about environmental conditions. In remote agricultural settings, sustainable food production depends heavily on efficient irrigation and fault-tolerant or robust energy systems. It's all good. Solar-powered microgrids offer a clean and independent solution for managing water, making the whole process valuable in rural regions. So far, so good. Everything is great, but despite their potential, these systems are usually prone to issues like sensor errors, electrical faults, unpredictable environmental changes, factors, and all these things can disrupt irrigation. And all these things can threaten the overall crop yields. Now, most traditional fault detection systems, like, threshold alarms or fixed rule-based methods, they're not really built to handle gradual failures or background noise, which are really, really common in the field. As a result, they often raise too many false alarms, or worse, they fail to detect slowly developing faults, especially in agricultural environments where conditions constantly change. And it makes it clear that we need smarter adaptive solutions that are specifically designed for the unique challenges of solar-powered agricultural microgrids. As far as our contributions are concerned, we have developed a new AI-based fault detection, so like a system of a detection system, let's say. It combines LoRaWAN enabled sensors with LSTM deep learning models for real-time analysis. Unlike many earlier studies, our system was actually tested and validated in a real agricultural environment, not just in simulation or lab settings. And our approach reached an impressive 95.4% accuracy, with fault detection happening in under 5 seconds. Now, apart from that, we try to explore edge computing feasibility and practical IoT implementation challenges throughout the whole process too. Let's talk about the system architecture. Our system is built around 4 main components, like LoRaWAN sensor nodes, a central gateway, cloud-based processing, and an AI model for fault detection. The sensors continuously collect key data in real time. It can be temperature, humidity, voltage levels, water flow, and stuff like that. And the collected data is then sent through the LoRaWAN network to the cloud, where we use LSTM-based models to detect anomalies and predict potential faults before they can become critical. Just because we are working with data, some pre-processing should be done on it as well, right? Now, we used sensors, as I told you just a while ago. Before feeding the collected sensor data into our model, we have to apply several pre-processing steps like noise reduction, normalization, outlier detection, trend extraction, to make sure that the input is clean and we can rely on it. Since we are working with the time series data, this pre-processing is crucial. And it basically helps the LSTM model learn meaningful patterns and detect faults relatively early. We collected data over a 3-month period to capture not just daily changes, but also seasonal and environmental variations as well. The table depicts actually the principal parameters observed by the system over that period of time. Now, experimental setup. In our setup, we trained the AI model using historical sensor data to recognize patterns that imply potential faults in the irrigation system. The process involves 4 main steps. First, we extract meaningful features like sensor trends. It can be deviations from expected values, seasonal shifts. Then on the second step, we train the LSTM-based deep learning model using labeled data, distinguishing between normal and faulty system behavior. Third, the trained model runs in real time, non-stop, continuously analyzing incoming data to detect anomalies and classify possible faults. Last but not least, when an issue is detected, the system sends a notification or an instant alert to the user, including a possible or likely cause of the problem. This framework was deployed and tested in a controlled agricultural environment, again, over a 3-month period, using these different sensors distributed across a solar-powered irrigation setup. The model's performance was evaluated using different parameters like accuracy, precision, recall, F1 score, right? And overall, our approach enables early intervention. It reduces the maintenance costs and it boosts the overall efficiency of a solar-powered irrigation system. Let's talk about the results and comparisons. Our AI-based fault detection system achieves an overall accuracy of 95.4%, as shown on the slide. It basically shows how strong of a performance it has in identifying faults in solar-powered irrigation systems. And as depicted in the confusion matrix, we reached a recall rate of 96.1%, which means the model successfully detects almost all the fault events. And it helps to prevent failures from going unnoticed, which happens a lot in traditional systems. We also maintained a precision of 94.8%, which reduces the number of false alarms and unnecessary maintenance costs or actions, right? Now, to put all these things into context, we compared our model to a traditional threshold-based or fixed rule-based detection method. The results clearly show that the AI model outperforms conventional approaches, which tend to produce more false positives and struggle with detecting slow or subtle faults. So what sets us apart from the others, what makes our system even more effective is its adaptability. Thanks to the LSTM model, it can handle seasonal patterns and environmental changes, which are common in agricultural environments. And it basically brings us to the end of the presentation. If you have any questions, we'll be more than glad to answer them. Thank you so much for your time.